Hello, this is the HP150. This particular unit has given me a lot of trouble the past few years. When it first arrived, it appeared dead, and I had to do a lot of debugging to find out exactly what was wrong with it. And after a lot of trouble, it finally worked, as you can see. However, there's still a problem with it. As you can see here, these labels should have been backlit in a backlit reverse video rectangle, like in ordinary HP terminals. And unfortunately, on this unit, it doesn't work. So we have to go and look at why the inverse video signal is not passed through to the display circuitry to make that rectangle appear in reverse video. So let's first look at the schematics to see exactly what is happening there. So this is one of the logic diagrams for the video PCA of the HP150, and this is the video controller for the alpha plane. There's another controller for the graphics plane, but we won't go into that. This controller generates the codes for the characters that are displayed on the screen, and these codes go to a ROM here, which generates the patterns. Since we have the correct characters displayed on the screen, we're interested only in the attributes, and specifically the inverse video attribute, which is generated by the attribute latch, which is an octal flip-flop, an LS374. So as we see here, the inverse video signal comes into pin 8, and it comes out on pin 9 as the IV signal, orange. Since this is a flip-flop, if we have an input signal and the clock ticks, then that signal should come out on the output pin. This particular chip has tri-state output, so it needs to be enabled in order to drive this output. But in this case, the output enable is always grounded, so the outputs are always enabled. I'm not sure why HP used a tri-state chip, but in reality it works like a normal flip-flop. The IV signal, which is orange here, goes all the way to another chip, which is referred to as an HAL1616 and is a custom HP chip. So if the problem is with this chip, then we are in trouble, because we will need to replace it with something that is probably no longer available. But if the problem is with the octal flip-flop, then we can replace that because it's still available. If the LS374 were socketed, I'd just replace it and see if the problem went away. But since I do not want to subject the board to the stress of desoldering devices unless it is really necessary, we need to determine whether this is really the problem or whether the problem lies downstream. The approach I use here is to take the inputs and use them to drive an identical chip and monitor the output. If the output is the same, then there is probably something wrong elsewhere. But if the outputs from the onboard chip and the new chip differ, then we know that the problem is on the orange path. Please note that it might be that this chip is not driving this line correctly, or it might be that something downstream is pulling the line low, so the video latch cannot pull it high. In this case, we would need to isolate this path by simply cutting off the output pin of the video latch, and then monitoring what comes out from the isolated pin to see if it matches the output from our new chip. If the outputs match, then we are in trouble, because then the problem is either on the HAL1616 IC or something along the orange path causes the line to be grounded. Looking at the schematics, this particular line doesn't seem to be connected to anything else, but it could be a short in the PCB. So if that is the case, we could isolate it by cutting that pin as well and putting a bypass wire to connect the input pin of the HAL1616 to the output pin of the LS374. So let's see whether the video latch is really working. Here we have the HP150 video display PCA, and this is placed in an extender board so that we can actually work on it. This is our suspect chip, the 374. And here is our new 374, which is going to be used to check the output of that one. So let us switch to the logic analyzer, which is connected to the little test board. This tells us that the problem is in the connection between the flip-flop and the custom chip. So the pin that we're interested in is pin 8. What I will do is to cut that pin, and I'll get back to you. Now with the pin cut, we can switch back to the logic analyzer and see that our device under test still reports 0. So now that we have isolated the output pin, it means that only the LS374 is driving that signal, and it is stuck low. Since the input to the HAL1616 is not driven, we can now connect that input pin to the new chip and see what happens. To do this, I'm going to take this wire and connect it to pin 8 of the new chip, and if we switch the display, we see now that the fields are correctly highlighted. So that essentially proves that our initial suspect, the flip-flop chip, was the chip that was not working. But that's not the end of our work, because now we have to remove the faulty chip and replace it with the working chip and hope that we don't break anything else in the process. I have now completed the replacement, and we can see that the highlighted fields are correctly displayed and the machine is now usable. The files you see displayed here are stored on an emulated MFM drive, and I will talk about that in a future video. And I also hope that I will be able to show you another repair of a video PCA board that is preventing the HP150 from booting. In the next video, I will show how we can debug that and hopefully how we can get that board working again. So thank you very much for watching this video, and until next time, take care.